Oh, went to the wrong thing. I don't know why it keeps going back there. Leave me where I am. Okay, the solutions. So we did not get 0 for our Wronskian. That means that set of functions is linearly independent. So that should say independent. This set was dependent. So this is the kind of stuff that's going to be on test 2. The Wronskian, calculating the Wronskian, determining if functions are linearly dependent or independent. Let's kind of open this up and talk through. If you get dependent, then that means there's some linear combination of the functions that equals 0. You can find constants, C's, so that multiples of the functions equal 0 when added up. So you might be asked to do this on the test. I'll give you some set of functions, and if they're linearly dependent, meaning you get 0 for the Wronskian, find some coefficients that make these guys add up to 0. You can't do that. That's impossible if they're linearly independent. Remember, that says independent. Then linear homogeneous with constant coefficients. We find our characteristic polynomial. We find our roots. Be on the lookout for repeated roots, which we treat a little differently, or complex roots. When, like this question here, all it asked for was the particular solution. You may still have to find you may still have to solve the homogeneous version and find your characteristic polynomial, because anything that's already used up for the homogeneous version can't be used again in your particular solutions. So this one, we don't have to worry about there. We know the homogeneous version. I mean, we just look at it. What does that factor? No, that doesn't factor. That would have complex solutions. But that's going to be exponentials and sines and cosines. Over here, our particular solution is going to be a quadratic. Like there's no conflict there. We don't even have, since they only asked for the particular, I don't even have to worry about what the homogeneous version gives me. Here I do, though. See, I know my particular solution is going to be some version of e to the 4x, but I got to make sure I didn't already use up e to the 4x from the characteristic polynomial. So I got to go ahead and solve that. Even though it didn't ask me to, I have to solve that, get my complementary function here, and I'm using -2 and -6. I didn't already use up e to the 4x. So I'm free to use that for the particular. If one of the solutions here had been lambda equals 4, then this would not work. I would need a x e to the 4x. If I had already used up e to the 4x twice, then I would need here a x squared e to the 4x. So you still have to solve the homogeneous version, get your complementary function just to check and make sure you haven't used whatever's here already up. Okay, that was a rational root theorem problem. Again, this used to be a take-home test. So, like, they had more time to do it. Okay, another, here we're finding the entire general solution. So we do, I mean, we just have to find our complementary function, all that. Here we're doing the same thing, but it's an IVP problem. A lot of mistakes happen here. on initial value problems. People will get here. They'll get their complementary function, solve the homogeneous version, set this thing equal to 0. They'll get here, get their C1 and C2 in something, and then they'll start plugging in conditions to solve for C1 and C2. That'll get you the wrong answer. You can't do that. You have to wait until the very end. That's your last step. So you need the particular function, the particular solution on there also before you start plugging in the initial conditions. See, here's one. Look what happened here. I've got over here on my non-homogeneous side an e to the 3x. So you might think, oh, my particular solution, one of them, is going to look like a e to the 3x. But it doesn't, because I've already used that up. I've already used up e to the 3x from the homogeneous version. So that guy's particular solution has to be x e to the 3x times a. And then going backwards. A lot of people have trouble with these, and I think these are kind of fun. So somebody gives you the solutions, then you know what your roots are. You can multiply those factors together to get your polynomial and then get your DE. So I know here my roots are going to be -1. Oh, look, somebody had to throw on an extra x. That means -1 was a repeated root. And 3. Those are the 3 roots to the characteristic polynomial. So those are my factors, x plus 1, and lambda, or I keep saying x, lambda plus 1 squared and lambda minus 3. When you multiply that all out, you get this polynomial, and in standard form. And then there are all my coefficients. Like the exponent will match up with the order of the derivative, and the coefficients come along, and that equals 0. And then this question, this one confused them that semester. I asked them to solve an IVP, and they wanted to go back to here. They wanted to start from scratch. We already have the solution. Like, we already know the solution. We don't have to solve the DE. We already have the solution. It looks like this. Now we plug all that in and solve our IVP. Okay, you can remember, you can always go back to old homework too.